Okay, we're going to do the PowerPoint presentation for day one. It's basically a review of DC and AC circuits. So let's pick up the PowerPoint presentation. Let's get the slide show. And here we go. So we'll do a review of DC and AC circuits. Start with the electrical fundamentals. Start with the definition of electricity, which we know is the flow of energy. Okay, where we have a source of energy, we flow that energy and that energy gets used up to perform certain functions, needed functions that we want. And in order for that energy to flow, it needs to be, it needs to go through materials that are either conductors or insulators. If they're a conductor, then we're talking about either metals or semiconductors, where metals have free electrons that can carry that energy. Semiconductors have much fewer electrons, but you'll get that in a future course. And they will conduct at a much lower level. The insulators, on the other, don't really conduct, but they hold energy. Okay, they can hold energy. They do that electrostatically. In other words, they hold a charge. And the insulators are usually made up of plastics or ceramics, and their chemical structure decides how much energy they can hold up. So, but we start out with electrical charges, which are the only two things that give us electrical charge are electrons and protons from an atom. Okay, and the electrons right now are the only things that are free to move around in case of a metal. But associated with either charged particles, okay, either electrons, protons, or an ionized atom, is an electric field. Okay, electric field is a vector, is a force field, making it a vector. And we will, this course is heavy on vectors, so we will go through vectors starting with probably tomorrow and so forth and on. So we're interested in electrical conduction, which is performed through metals, because metals have immobile charged atoms, but they have mobile negatively charged electrons. And metals stay together because they have a pool of electrons inside them that are easy to move around. So if you place a metal inside an electric field, then you're going to get some electricity. We are pretty familiar with that. So there are two models of electricity. The book likes to use the physical model, which is the charge flow model, where electrons are flowing from a negative to a positive, okay, because electrons are negatively charged and they want to go to a positive area, so they move from and you get an electron flow. However, electricity, and everybody uses the conventional model because electricity, like I mentioned, is energy flow, okay? And the energy flow model, which is the conventional model, it tells us that energy flows from a higher energy potential to a lower potential. So as shown here, you can think of it as water being the electrons that are flowing through a pipe, which is the conductor, goes from a reservoir of a battery reservoir, essentially, holds all the charge, to ground, which is the low potential. And the flow is from the high to the low. But in order for it to flow, we need to describe a number of different variables. We start out with the charge because that's where everything starts out with. The charge is given the letter Q, and it's measured in coulombs, okay? Voltage is the way, is a requirement that's needed to get some current to flow. So it defines the amount of work that's needed per the unit of charge. So V equals W over K, where W is the work and Q is the amount of charge that's used to carry that work. Current then is the amount of that flow of those charged particles. So current I is equal to the number of coulombs divided by the time. I mean, how many coulombs are transferred in a unit of time in a second? That's current. But of course, we want to know the energy transfer, and for that we use the rate of the energy transfer, which we call power, which is the voltage times the current. The current is the movement part of it. The voltage is the charge part of it. So when you multiply the two together, you get watts. And those energy that could be a true useful power energy, which is what we use in DC circuits. But when we got to AC circuits, we used just voltage times current to get volt amps. So, and that's basically that could be a reactive power. Another basic parameter is the conductance and its reciprocal resistance. Of course, we use the resistance more than we use the conductance. The resistance basically is the parameter that opposes the electrical conduction. And that's measured in ohms, okay? Ohms, and the reciprocal of ohms is the unit of Siemens, which is the conductance. So now we get to the first step, is we've got to create a circuit. Okay, a circuit made up of at least a power element and some electrical components that are wired together or conductively together. Okay, we can use wired assemblies, which means that we're just taking individual components and using wires to connect everything up. But of course, the more standard way is to use a PWB, or which we call a printed wiring board. But as we actually put it together, we call it a CCA, or circuit card assembly, because we have a card and we're placing components on it, and then we solder the components together. And when we solder them, we basically solder them to essentially solder wires, solder paths. Okay. So first, let's get into DC circuits. DC circuits, we know, are unidirectional. That is, the voltage and the current is always in one direction. Okay. For when we use the physical model, it goes from negative to positive, but when we use the energy flow model, the conventional model is to go from high voltage to low voltage. DC components that we use are, first of all, the source of power is a battery or a power supply, which has a positive and negative end. Wires that create our conductive paths on a board. Or resistors that are the components that limit the current, and what they do is they dissipate some of that voltage and dissipate the power. And then capacitor, but that's a non-standard component in a DC circuit, but it is used where we need to maintain a constant voltage or to actually maintain a charge. And we learned all about Ohm's law, which we can write up as voltage equals current times resistance, or we start with that one because that's really the basic Ohm's law is V equals IR. When people talk about Ohm's law, they're really saying V equals IR. And you can take that equation and then make it into I equals V over R, or R equals V over I. Okay. And because it's electrical and because we're distributing energy, we also get a distribution of voltage. So across as a conducting component, such as a resistor, we get what we call a voltage drop. Okay, in other words, it's got to go from a higher voltage to a lower voltage. So there's a voltage drop in the direction of the current, in the direction of the energy model of the current, okay? So the voltage decreases from positive side to the negative side because we're using the conventional model. And we can talk about an equivalent voltage, which is a net geometric sum of all the voltages. In other words, we could have more than one voltage source, okay? And those voltage sources can be opposite one another, or they can add up. In either case, you add the geometric sum to get an equivalent voltage for that particular DC circuit. So the total current depends on what that net equivalent voltage is, and divide that by the effective resistance. So IT equals V equivalent divided by effective resistance. So here's our first very simple series circuit. Call it a series circuit because the components are hooked up one after the other in a series fashion. So we start out in here, we've got a 24 volt source, and we've got 4 resistors of different resistance values. And to analyze the circuit, then we could have different voltages at points A, B, and C, and other points as well. But just as an exercise, we can figure out what those voltages are at points A, B, and C. So in order to do that, we start out with, we have to determine what the current is. This is a series circuit, so the one current only, and it goes through all the resistors. So the first, in order to figure out what the current is, we need to know what the effective or total resistance is. So if we add up all the resistances, because it's in series, we get 20k ohms of resistance going through that whole circuit. And so the current then is going to be the 24 volts divided by the total resistance, giving us 1.2 milliamps of DC current. And so we have the current is 1.2 milliamps. Okay, it starts out from the VT, our battery. It goes first through R1, and when it goes through R1, okay, we get a voltage drop from 24 volts minus the current times R1. Okay, so that gives us our value of VA 24 minus 10K times 1.2 milliamps, or 12 volts. So point A is at 12 volts. Then we drop even further by going through R2. We drop there's our current 1.2 milliamps, and our resistance is 75K, okay? So we 75K times 1.2 milliamps, and we start out, we had 12 volts up here. We're going to drop another, it looks like another 9 volts to get to 3 volts when we get to B, okay? Look, we had 12 volts here, we get to 3 volts here. It means we have dropped 9 volts across R2. Then we drop another bunch of volts from going through R3, which is 15 or 15K, or 1.5K times 1.2 million. So we get, at point C, we get 1.2 volts DC. Okay, there's our voltage drops in a series circuit. And if you were to add up all the voltage drops, you would find out that the voltage drops is going to total of voltage drops is going to be equal to 24 volts. To that, we switch to a circuit where we have a capacitor and a resistor. Okay, and basically, when we trip the switch here, okay, once we trip that switch, then the voltage will be felt first by the resistor and then by the capacitor. And initially, then the capacitor is basically an open circuit, but it's going to be charged up. And it's going to be charged up initially by a current that's Vs divided by R, okay? And the rate at which the capacitor charges is related to the time constant, as we call time constant being the product of the resistor and the capacitance. And we know that it takes, and if you multiply resistance times capacitance, we get a figure that's in seconds. So it takes the time constant is going to be some numerical value in seconds or microseconds or whatever, but 5 times that time constant is what's needed to completely charge or completely discharge going the other way of that capacitor. Okay, so let's look at a DC parallel resistor circuit. All right, now we have basically 2 paths for that 90 volts to travel to empty some energy. We've got the path going through R1 or the path going through R2 and R3. R2 and R3 we can know are in series, so we can add those up. So this gives us an equivalent of 20 plus 25, 45 ohms, okay? And R1 is just a 30 ohms, so we get, we want to find out what all currents and the voltages are. So first we want to figure out, okay, how much of current do we need? Well, we know that 30 volts or 30 ohms is going to be in parallel to 45 ohms. So we can get an equivalent resistance value using our regular standard parallel resistance equation, 30 to the 1 over 30 plus 1 over 45, take the total and then take the reciprocal of that to give us an 18 ohm value. So that our total current then is going to be the applied voltage, 90 volts, divided by that 18 ohms or 5 amps. So initially coming out of this battery or this voltage source is 5 amps. Okay. So, but since this is a parallel circuit, we know that 90 volts will be across R1, and 90 volts will also be across the combination of R2 plus R3. So we can figure out what the different currents are, I1, and what the current through 2 and 3. The current through I1 is just basically VA divided by R1, or 3 amps. So we got 3 amps going through R1. And we don't really need to go any further than that, because if we know that 3 amps is going through R1, then that only gives, and we start out with 5 amps, okay, then what goes through I2 and I2, 3 has got to be 5 minus 3, or 2 amps, okay, which we can figure out either by subtracting or by taking it 90 volts divided by 45 ohms to get 2 amps. And then shows also again that Kirchhoff's current law is satisfied because the sum of I1 and I2, 3 is equal to I total. Okay, now we create, from that we went to, okay, supposing you got a combination of series and parallel circuit, okay? So, and we want to find out what is the currents and voltages, all the currents and all of the voltages. Well, we do this by realizing that we can reduce this whole circuit, can also be reduced down to an equivalent series circuit. So first we find an equivalent resistance, figuring resistor, where are we here? Resistor 1, 2, and 3. What's the equivalent? So we notice that R2 and R1 are in parallel to R3, okay? So R2 plus R1 is 8 plus 8 is 16. So 16 ohms is parallel to 16 ohms. Well, if 16 ohms is parallel to 16 ohms, the equivalent is half of 16, or 8 ohms. Okay, so this portion of the circuit becomes a resistor of 8 ohms. So we got 8 ohms. Imagine 8 ohms going down from V4, from R4 down to here. Okay, so we've got then, in this case, we're going to figure out the equivalent resistance with 5, 4, and the 8 ohm resistors here. So, but 8 is in series with the 12, giving us 20. Okay, so we got 20 ohms in parallel again with 20 ohms. Okay, and so that gives us this is wrong. This gives us an equivalent of 10 ohms, actually. All right, gives us 10 ohms. And so we've got 10 ohms, again, in series with 10 ohms. We got 20 ohms. Okay, that's what this is. 10 ohms plus 10 ohms gives us 20 ohms. So a total current of, a total resistance of 20 ohms divided into the voltage of 80 volts gives us 4 amps. So this battery here, VT, it supplies 4 amps in total. All right. And then we work it backwards to figure out what each of the different, if we go back, figure out, okay, we had 10 ohms across here. So we know what the current then going through the R6 has got to be 4 amps, right? And what goes through R5 then is going to be, well, whatever the 80 volts minus the IO drop across V6, okay? And we continue going backwards that way. If we have a simple capacitance circuit, then there are two. We can have those capacitors in series or in parallel. Okay, and we use these equations. We figured out what the equations are to figure out what the voltages are for across each of these capacitors if we had 900 volts. Okay, and I would copy these procedures. The other way of doing it, though, is actually knowing that if capacitors are in series, okay, they work the opposite way the resistors are. So capacitors in series give you that reciprocal that 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 quantity reciprocal of that. Okay. But for parallel systems, parallel capacitors, they're basically in series. It makes it look like they're in series. They're addition. They add to one another. Okay, so, but that's simply DC-wise, all right, if we have a DC. But capacitors are mainly used in AC circuits and circuits with changing and repetitive voltage and current time. So basically, AC circuits are time-varying circuits where both the voltage and the current varies in time. Picture here our graphic. DC voltage is in red. The current is reduced by the resistance value, okay? So that the current is 8 amps, for example, here, okay? Where the voltage is 15 volts. So you can figure out what would be the resistance. The resistance would be V equals IR, or R equals V over I. So 15 divided by 8, okay? So that gives us a resistance. Or in AC wise, we've got a varying voltage given by the red curve. And if and these are showing a peak of 15 volt peak on the positive half cycle and a minus 15 volts on a negative half cycle. And the current then it would be, if it's 15 to 8 here, it's going to be 15 peak here to 8 peak here, AC wise. There's the blue dotted is going to be our current. So, but we need to figure out, okay, if everything is changing in time, we need to use different parameters. We can't use the same type of parameters that we use in DC. In DC, we just say voltage, we don't care about time. And current, it's amperage, we don't care about time. But here, we do care about time. So first thing we define is a frequency. And if we go back, we notice that the curve here repeats itself. Once it goes beyond this, we repeat the circle again. So we call it, how often does this repeat itself? That's what we call a frequency. How often in time does a voltage or a current repeats in 1 second? And that's given in terms of hertz, Hz, cycle, which is also known as high cycles per second. The reciprocal of that is a period, which is the time of 1 cycle. So if you knew what the frequency was, you just take the reciprocal of the frequency to get its period. If you knew what the period was, you take the reciprocal of the period to get the frequency, okay? And amplitude is that maximum value, okay? That's that peak value, okay? Also called a peak value. And we have a peak value in current, and we have a peak value in voltage. Right? So the peak value is the amplitude of voltage or current parameter. We can have a value which we call peak to peak, which is from the positive side to the negative peak. So that's twice a peak value, normally, if it's a regular sinusoidal curve, okay? And then there's the parameter that's more important to us called the root mean square parameter, or RMS value. Use the RMS values, magnitude value of voltage and current, which is equivalent to matching a DC value used in evaluating the true power. So if you do that, you find out, if you go through the analysis, you find out that the RMS value of the voltage or the current is 0.707 times the peak value of the voltage or current. So V peak or V RMS is equal to 0.707 of V peak, and I RMS is equal to 0.707 I peak times I peak. And then finally, we have a phase, which is a timing difference between two varying AC signal, AC parameters, and we express that using an angle, normally theta. We know that AC-wise, you've got different electrical waveforms that you can use. The one that we are using for the book mostly is the sinusoidal wave, okay, which is, this one is sinusoidal, one peak, two waves, three waves. So basically we show 3 cycles, okay? Or we can have a square wave, which we use for digital components. Or we have a triangular waveform and also a pulsed linear variation. These are all periodic. They have a period associated with them, all right? But the standard AC signal that we studying are basically a sinusoidal signal. And we found out in the last course that it's sinusoidal because of the way it's created, okay? When you have a circular motion, that circular motion is defined by a sine curve, okay? Or if it's a pendulum motion, okay, pendulum motion, it's also a sine curve, okay? So one cycle that's expressed as an angle of 360 degrees, or in radians, it's 2 pi. So we express that, we have frequency, we express that in hertz, and time in seconds is t. Amplitude is given by a peak value normally, or we can also use RMS value if you want, but V peak or I peak. And then we have voltage as a sinusoidal function or current as a sinusoidal function. And we also know that 90 degrees is equivalent to pi over 2 radians. Okay, pi over 2 radians. So that 2 pi times f times t is essentially pi over 2. Okay, so the t basically is a 1 over 4 times the frequency, or a quarter of its period. Okay. Here's our standard curve. We've got the first half cycle gives us a positive. The second half cycle gives us a negative peak value. Okay, we got the first 90 degrees to get it to a maximum. And during the second 90 degrees, we go down to 0, and we build back up in the opposite sense during the second half cycle, and then back to 0. So we start at 0 and end at 0, giving us one full cycle. So if you take an AC resistor, so if you take a AC circuits with just plain resistors, we use voltages are in terms of volts times AC voltages and currents. Then from VAC, we get IAC. The power must be evaluated using RMS. So what we do, we take VAC, the peak value of the voltage multiplied by 0.707 to get RMS value. And we can at that point also figure out what the IRMS value is going to be by just divided by the resistors, by the resistance. Or if we know what the peak value of current is, then we multiply that by 0.707 to get IRMS. And then standard DC rules apply. So voltages and currents are in phase, though. There's no phase differences. So voltage and current occur at the same time sequence. So responses between voltage and currents are immediate. In other words, they're non-reactive. There's no reaction. Resistor doesn't cause any kind of reaction. Reactive components, on the other hand, are capacitors and inductors. Capacitors measured in farads, and basically they store energy by an electric field. The stored energy is equivalent given by a half times the capacitance times the voltage squared. So depending on how much voltage there is, the total energy stored by a capacitor of capacitance C is a half CV squared. And there's an effective resistance, which we call a capacitive reactance. This is basically resistance, like a resistance value measured also in ohms, but it's reactive. It's not, there's going to be a difference in phase. And that value is going to be inversely proportional to the frequency and the capacitance value for a capacitor, but directly proportional to the frequency and the inductance for an inductor. An inductor measured in henries, and the inductor stores its energy as a magnetic field, magnetization, and its stored energy is a half L times I squared, okay? And there's effective resistance given by XL and 2 pi FL. The time constant for charging and discharging a capacitor is R times C, whereas the time constant for an inductor is L divided by R. Both of those values give you numbers in terms of seconds or microseconds or whatever, and it takes 5 of those time constants to fully charge or discharge the particular units. So dependencies, in terms of capacitance, we have charging current depends on the time changes in voltage. So you have to have a time changing in voltage to create charging, but they stop DC, but they pass higher frequencies. This is where we'll explore that in detail next week. Okay. What we get, though, is that voltage lags current by 90 degrees in the terms of a capacitance. So what this really says is that you need to charge it up first before you get a voltage. So current leads the voltage. You charge it up and you get a voltage. Whereas in the case of an inductance, it's the opposite. The voltage depends on the time changes in current and not the time changes in voltage. So it passes DC and lower frequency voltages, but the current lags its voltage by 90 degrees. So the inductor looks for a voltage change to create a current. Okay, so the voltage leads the current by 90 degrees in the case of an inductance. So pictorially or graphically, this is what it looks like. For a circuit where you have a RMS voltage of 15 with a resistor and a cap with effective 5 ohm resistance, this is just to play RC circuit, and you get the current is leading the voltage, okay? Because you notice the current starts at a higher value than the voltage does. So current is leading, while the voltage then lags by 90 degrees. And why is it 90 degrees? Well, you can see the current goes to 0 at the 90 degrees, and at 90 degrees, the voltage is built up to its maximum, okay? And again, you see the same thing happening at 270, all right? So from this, we create a phasor system that we use to describe voltages and currents, to analyze what the voltages and currents are, resistive and reactive elements, when timing is a factor. In other words, we can't really say that a capacitor has so many resistance, but we say it has a reactance because its voltage and its current are not in phase. And the same thing with inductors. So we use a reference, which is your horizontal x-axis as our reference. Normally that's our resistor or our true voltage, or the applied voltage, okay? And the voltages that are either leading in the case of an inductor or lagging in the case of a capacitor, okay? Or if we have this as current, then leading current would be for capacitive leading, okay? And inductive lagging current. That's our phasor system. So series circuits are all about total current. In other words, if you have a series circuit, no matter what components are in there, there's one current that flows through all of those, okay? All about the total current. And we have, if you have total current, we've got voltage division. So we've got resistance voltages and we've got reactive voltages, VR and VX. But the total current runs through all components, and a circuit effective resistance is labeled as an impedance. So, both VR and VX, or both resistance and reactance, contribute to total impedance. And we figure out what the total impedance is by taking the square root of R squared plus reactive squared. And we can do that doing a impedance circuit, phasor. So in the case of an RC circuit, we've got R being where everything measured, that's our relative component, R. XC is behind it, lagging, okay? And we take r squared plus x squared, take the square root of that to give us our z, our impedance. And similarly for an RL circuit, this would be R along here and XL up, okay? Because yeah, all right. Series current, the current runs through all the components and is determined by the total voltage and the circuit impedance. So we wanted to figure out what the total current is in a series circuit. If we find out what the impedance is of that circuit, then we just multiply it into the applied voltage to get a total current. Parallel circuits, though, are all about total voltage and current division. In other words, we have voltage being supplied to the different branches of a parallel circuit. So each branch has the same applied voltage, VA. So if we've got a capacitor or a reactive component in parallel to the resistive component, then the current through the resistor part is just VA over R, and the current through the the reactive component is VA over the reactance. So the applied voltage is VA is the same across both the parallel branches, and the circuit impedance sequence is determined from the applied voltage and the total current. Okay. So in this case, we use current phasors to figure out what the total current is. Okay, so we've got a capacitive current and a resistive current. Okay, so in the case of parallel circuits, then we use the individual currents as phasors to figure out what the total current is. Okay, so once we figure out what the total currents are, then we can go back and figure out what the impedance is. Okay, and basically we can figure out what the angle is also by taking the arctangent. So principal equation again for impedance, the equivalent is VA divided by I tau. VA is whatever is applied, voltage is applied, whatever the battery voltage is, or source voltage, not a battery. Okay, and IT is what we just figured out using the phaser. We can actually figure out for an RC circuit, we can figure out XC times R divided by the square root of R squared plus X squared. Okay? And we do the same for XL. So let's look at some alternating current circuits, chapter 23. We can use the phasor method. XS is taken as the applied voltage that's in phase with the resistor. Parameters that lead the reference by 90 degrees are on the positive y-axis and have a positive angle of theta, whereas those that are lagging by 90 degrees are on the negative y-axis and have a negative angle theta. Oops. Vectors are aligned in the same direction are added to obtain a net reactance. Okay. So if vectors go in the same direction, of course they add. But non-reactive circuits contain only resistive components. So there's no XL or XC terms, and all voltages and currents are in phase. So the DC calculation methods of totals and equivalents are applicable, so we don't need to use phasors. Voltage and current units apply. So we don't need to say phase differences. But if we have circuits with only inductors, in the case of a series voltage, we get voltage division. Total reactance is XLT, which is basically the sum of all inductive reactances. The same current runs through all the inductors, and there will be individual voltage drops, just as there are in IR in a DC system. Okay, given by I times the individual reactive, and the individual voltage leads the current by 90 degrees. Parallel-wise, we have current division. So the applied voltage is applied to the same across each branch, and the individual branches will have individual branch currents and individual current and voltages. Okay. So series XL example, here's one where we've got two inductors in series. Just add those two up to give us a total of 100 ohms. So the total current is just going to be 100 volts divided by 100 ohms to give 1 amp. So the VL, the voltage drop across each one, since XL1 is equal to XL2, they're going to have the same voltage, which is 1 amp times 50 ohms, or 50 volts. 50 volts. If we have a parallel situation now we have to use currents. We've got current division. So we're going to have, since XL1 and XL2 are the same or equal, then the same current I1 is equal to I2. It's just going to be 100 divided by 50, 2 amps. So we got 2 amps going across each circuit, each branch. Both are lagging current, 2 amps by minus 90 degrees from VA. Okay, so it could be a total of 4 amps in all. All right. So now we switch to circuits with only capacitors. Total reactance is going to be the sum of the XCs. The current is going to be determined from the ratio of voltage to reactance. Okay, but in this case, we're going to have individual VIs are lagging the current by 90 degrees. Parallel-wise, again, we have the same voltage applied to each branch, and each individual branch will have its individual current that's going to be leading the voltage by 90 degrees. So here's a case of series, okay? So again, because it's in series, okay, because it's in series in this case, we can add the two XC1 and XC2 to give us 100 ohms again. So we get 1 amp again. 1 amp is going to go through both of those, okay? And through each one of those, it's 1 amp times 50 ohms or 50 volts. That is the voltage drop across capacitor 1 and across capacitor 2. We put them in parallel. Again, we're going to have, and because the reactances are the same, we're going to have equal currents. And again, 50 ohms divided into 100 volts, giving us 2 amps. So both currents are going to be 2 amps and be at plus 90 degree leading from VA. Okay. So, but if supposing we combine the capacitor and inductor, well, the capacitor current leads by 90 degrees, whereas inductor voltage leads the current by 90 degrees. So reactance results, they oppose each other, okay? One lies and the other leads. So the interaction, then the total interaction, it depends on which one is going to be stronger. So if XL is greater than XC, then circuit net effect is going to be XL. It's going to be inductive. Whereas the opposite is true if XC is greater than XL. Okay, so here we go. We've got a 40 ohm cap and a 60 ohm inductance. So the inductance is greater, the reactance is greater than the capacitance. So that gives us plus XL minus XC, 20 ohm inductive XL. Net effect is going to be an inductive XL. So 20 into 120 volts will give us a current of 6 amps. Here we go. So we've got 20 amps. Yeah, 6. There we go. 26 amps. Then 6 amps goes through XC. It gives us 240 volts. 6 amps is still going to go through XL. 6 times 360 volts. Phase VC and VL. VC is at minus 90 degrees, where VL is at plus 90 degrees. So the net, and then the net voltage, though, is 6 times 20 or 120 volts. Okay. Okay, so supposing they're in parallel with no resistors. Again, we do this, if it's parallel, we're in a current situation, right? So we do a current situation, determine currents and relative current phases. So IC is going to be 120 over 40, or 3 amps, with leading, 90 degree leading. And where IL, though, is going to be 12 over 60, 2 amps with 90 degree lagging. Okay, determining that current, and then is 3 leading, 2 lagging, giving 1 amp leading. Okay, what's the net reactance? Oops. Net voltage, net reactance is going to be 60 minus 40 or 20, where XL is leading. So here's a picture of what it would look like, and it's kind of weird to take a look at it. It's very confusing, but basically you've got, looking at a reduced, in order to show them all on a certain figure, had to reduce the applied voltage, okay, to show it as a dashed dark lighted line. But we've got our leading capacitance current and lagging inductive current. Okay, that's what that picture shows, the waveform. So circuits with resistance and reactance. We know that in the resistive element, the voltage and current are phases. The capacitor voltage lags by 90 degrees. So we get minus 90 degrees, where an inductor voltage leads the current. So we get plus 90 degrees. And the capacitor reactance and inductor reactance oppose each other. So we take the magnitude of XL minus XC. And the effective resistance then is the impedance, which is the square root of R squared minus X net squared. And again, we use phasor coordinate in the same way, same phasor diagram. So we've got series resistance and reactance. Supposing we had three components, okay, got 100 volts AC applied to a series circuit that has a 40 ohm resistor, a 90 ohm capacitor, and a 60 ohm inductance. So we combine the reactances to get a net of 60 minus 90, giving us minus 30, okay? Because 60 is leading, 60 is leading, minus 90 being behind. So it's lagging 90, so we get minus 30 as a net reactance. From that, we can figure out what the impedance is. We get the R squared, 40 squared, plus minus 30 squared, taking the square root of that gives us 50 ohms. So determine current and voltage drops. Current is equal to the VA divided by Z, 2 amps. The voltage across the resistor is 2 times 40, 80 volts. Across the inductor is 2 times, sorry. All right, I have this backwards. This should be VC, 2 times 90 is the voltage across the capacitance, and that's equivalent, this is 120 is across the inductance. I have these backwards. So the phase angle then is minus 30 over 40, okay? Minus 30 over 40 gives us a minus 37 degrees. If we have a more complicated one, do the same thing. Add up all the resistor values, add up all the inductive values, no, capacitive values. Okay, well, let's see what we have. X net. Okay, we've got minus 70 is the first one, and minus 20, giving us minus 90. And then for the inductors, we've got just the 30, unless there's another. Oh, there's two 30s, so 30 and 30, okay? So we've got 30 and 30 are 60, minus 90 plus, so we got minus 60, so it's capacitive. Determine the impedance, where R is equals to 40. So again, 40 and 60, giving us 72 ohms. And the current voltage drops. The current is 100 divided by 72 ohms, 1.4 amps. So 1.4 amps goes through this entire circuit, and the voltage drops then accordingly to depending on what those are. And of course, the angle, phase angle, is minus 56, which is the reactive divided by the resistance. Okay. Just dual subscript notation. If I give you what is the meaning of VAB, the meaning is what's the voltage at point A relative to the voltage at point B. And so using the digital multimeter, we use a red probe to put it on point A. Put the black probe at a point B gives the answer in the meter. So it'll give you what the voltage of A is relative to B. Okay, because they put the black probe at B. So if we reverse the order of the subscript, it basically reverses the sign. In other words, if we took a measurement of A and B, okay, we got a measurement, then we reversed the probes, we get the negative number instead of the positive number. It'd be the negative of each other. Okay, but so now supposing we have parallel situation, resistance and reactance, and again, parallel situation means current division, right? Current division. So first we got to determine the branch current. Then we combine the reactive currents and determine the effective net reactance and net reactive current. Then we determine the total current and the phase angle relative to VA. And then finally we determine the impedance. So, okay, first thing, current division, we know across the R, it's just 25 into 100, 4 amps. Across the capacitor, it's 100 divided by 100. We get 1 amp at plus 90 angle. Across the inductor, it's 100 divided by 25, or 4 amps, but at a minus 90 degree. So the net reactive is we got plus 1 amp and minus 4 amps inductance. So we get minus 3 amps inductive. So basically the fact that, well, you can see here that XL is lots smaller than XC. So it's going to be mostly inductive, and it's going to be minus 3 amps inductive. So the net inductive is 3 amps divided into 100 volts, or 33 1/3 ohms. So that is our net inductance, net reactive component. Okay, and therefore our total current then is going to be R squared plus X, 3 amps squared plus 4 amps squared, square root of, to give us a 5 amp again, with a phase angle of arctangent of minus 3, the reactive divided by resistive. Okay, and our Z, our impedance then, is going to be the voltage A divided by the total current, which we got from here, which was 5, and so it's 20 ohms. And we could do something similar using a 6-component parallel circuit. And we do essentially, best way to do that is to create a little table, okay, to get everything done. So in case we have series parallel circuits, we do that by reducing the circuit to a simpler series circuit as we did before, and to obtain all the other variables. Okay, do series reactance, total currents, phase angles. Okay, so here's a case where we create, we can create these two as 100 ohms. Okay, and first we create, this guy is going to be 600 ohm versus 400 ohms. The difference is 200 ohms. Okay, 200 ohm inductive because the inductor is greater than the capacitive. Here, this is totally inductive, so you add those two to 200. But 200 in parallel with 200 is going to give you a 100, right? 100. So result in series with B100 and 100 in series. So we get to that. So this is our equivalent circuit. And then we would determine what the impedance is. The impedance, the current, just by dividing the impedance into the voltage to get a current, and so forth. And we continue again to go backwards that way. And if we use purely resistive circuits for power determination, we get powers in watts, I times V, or I squared times R total. But in I and V and DC units, or in RMS units for AC, but I and V are in phase. So power is stored as heat and is not reversible. For circuits with reactive components, though, I and V are not in phase and except through the resistive portions of it. So in power, then in AC circuit, we store energy, stored elements, such as we do in capacitors and inductors, result in periodic reversals. And the direction of the energy flow is changing. So we have real power, which is that portion of the power that flows over a complete cycle of AC waveform. So there's a net transfer of energy in only one direction. So that's the active power. Then there's the reactive power, that's the only portion that flows back and forth. Okay? And then the apparent power, which is a net effect of both of those. So we can define what the parameters are by math, okay? Or we can use the power triangle and come up with something which we call a power factor, which is the ratio of the real power to the apparent power. And that is it. If you want to go over this more carefully, you can do that by just looking at the pure PowerPoint presentation.